So far we've been looking at limits considering values of x that are finite and seeing what their limits are. But now we're going to start moving to what happens when we have very large numbers or very small numbers for x. So we're looking basically at positive infinity and negative infinity. What we're looking for is if we're going to be balancing out, leveling out at some horizontal asymptote line, or if the values are going to keep growing, like going up to positive infinity, or maybe going down to negative infinity. And one thing to pay attention to is if I'm plugging in larger and larger values for x, that these numbers are going to keep getting closer and closer to 0. So that would be our limit as n is approaching infinity. However, if we plug in a very large number in the top and bottom of an equation like this, I'm going to have a very large number over a very large number. And so what's going to happen is this number so much bigger, or is the bottom number bigger in a way that it's going to go maybe to 0 or maybe some other finite value. Maybe it'll divide and be 1. But it's possible that one's growing faster than the other one. Same problem's happening over here. We've got infinity over infinity. Now in both of these, if you plug them into a table in your calculator, you would see that they're tending, well, this one tending to a certain value of 2/5, whereas this one's growing to a much larger number. Now there's a way that we can check and tell, and it's dealing with something called end behavior models. Kind of the idea behind this is if you look at just the largest term in each of these. Okay, now this one's just 3x to the 4th, but this one's got a little bit of extra stuff in it. If we compare these in a small window, then we'll see that they're actually pretty different. However, if we zoom way out, they look pretty much the same because on the ends, when they get so large, only the largest polynomial term, the one with the largest exponent, is going to take over. Another way that we can think about this is if we made a fraction out of it, putting it all over 3x to the 4th, notice how this would cancel out. We would have the 3x over 4th giving us 1. These would all leave an x in the denominator. So if I'm putting in very large values for x, each of those is going to go to 0, leaving us only with the first two terms going together. Since I had 3 over 3, we're just getting 1. This is called an end behavior model, and there's a really formal definition of it. The end behavior is some function g that we can choose so that when we divide it, overall it gives us 1. Basically, in these polynomial functions, that end behavior function was just the largest power term. Now if we want to choose then an end behavior model, we want to usually take the highest degree in both the numerator and denominator if they're giving us a fraction-like term. For example, these two I have in the top, in the numerator I have 2x to the 5th, and the denominator 3x squared is the largest exponent. So if I'm looking for the end behavior model and thinking about, for example, the limit as x is approaching infinity, or positive or negative infinity in this case, then I would be thinking about 2x to the 5th over 3x squared, giving me 2x cubed over 3 when we cancel that out. Now notice then when we plug in either positive or negative infinity, very large numbers, this is just going to keep growing, or in the negative side, keep going down. In the other one, if we look at the largest power term in both the top and bottom, that's going to give me 2x cubed over 5x to the 3rd. That's going to leave me with 2/5, and so if I took a limit here, no matter which side I go on, I'm going to have a horizontal asymptote line of 2/5. What's happening in both of these is that this term, since I have a 3 from my exponent, it's going to be growing so much faster than things with a smaller exponent. Now some basic graphs to know for end behavior is, for one, the e to the x function, the exponential function. It's going to grow really, really fast. And it's going to be growing a lot faster than just normal polynomial functions. Okay, so it's always going to take over something like x squared. Notice though on the negative side though, this thing's going to go to 0. And so it's not going to be as important on this side. This side it grows very fast, the other side it goes to 0. If we have e to the negative x, that's going to be flipped around, where for negative values we're going to grow very fast. For positive values it's going to go to 0. Our natural log function, since it's the inverse of that, It's actually going to have a vertical asymptote line here, but we still want to know what this does, be familiar with this graph. In terms of our in-behavior models, it's actually pretty weak because it's not going to grow very fast. So most polynomial function, maybe even x, would be stronger than this because x is going to keep growing at a constant rate, whereas this is really slowing down. Same thing with absolute value of x, except it's going on both sides. So if we're looking for in-behavior, in a problem like this, I have x plus e to the x. My main question is, which one is going to grow faster? Which one's more powerful? Which one's going to grow? Now, as we just looked at for this e to the x, it's going to depend on whether we're talking about positive values or negative values. So for positive values here, this e to the x is going to be growing so much faster than x that when we get to very large values, the x is almost not really going to make a difference. It's going to be a huge number plus a big number, which is going to be a huge number. So for positive values, our power here is coming from e to the x. For negative values, though, when we think about plugging in negative values to the e to the x function, well, since those are negative values, then that is going to be going basically to 0. But x is going to keep going down. So if we want to know what's happening for the end behavior, we want to follow x, because basically we're looking at x plus 0. If we plug this thing into our graphing calculator, our graph looks basically like this. So notice how on the right we have a close similarity to e to the x. So that's our in-behavior model, y equals e to the x. On the left, however, notice how much this resembles the line y equals x. And so that's our in-behavior model. Okay, one last problem that we'll look at on this one is the sine of 1 over x. Now, if we look at sine of 1 over x, we might be able to see from the graph here what this is doing is we're getting further and further away from 0. Now, while this may not follow what we've been doing before, but we could just think about the fact that 1 over x is going to go to 0. So as I plug in those values, I could plug this in and know that this is going to sine of 0. And so as we're approaching infinity, or the same thing for negative infinity, we just look at the sine of 0 and we can see that this is going to 0.